Okay, so here's some more guessing games with geometric sums. I put up the two that we figured out in the last video, and here's a classic one, just the sum of the powers of 2. I'm not contriving this to be some special number here, although it actually turns out to be exactly what we want for a simple answer. And let's just list what the partial sums are. 1, 3, 7, 1 plus 2 plus 4, then add 8, you get 15, then add a 16, which is missing there, 31, add a 32, you get a 63. And then we just want to see, are these numbers special? Good place to pause the video, although there's a huge, huge hint in terms of these answers up here. And the way I would describe it is these numbers themselves, the powers of 2, are clearly special in the problem. We might want to think about how these compare to powers of 2. Oh, wait a minute. This is 1 less than that. Oh, and this is 1 less than that. This is 8 minus 1. This is 16 minus 1. This is 32 minus 1. This is 64 minus 1. I think we've got our answer. And this is maybe the classic example that if you sum up the powers of 2 up to, say, this is 1 plus 2, and then that was ending with a 32 as the last one, you just get exactly the next power of 2 minus 1. And so if you express that as a formula, the next power of 2 beyond the one we didn't use, beyond the last one we did use, rather, is 2 to the n, and then minus 1. So for example here, like this one, that's 1 plus 2, a very small dot dot dot, plus 2 to the 4 minus 1. The last one we added here was an 8. That's the fourth term. Let me just put that in, right? That's, maybe just write it as 2 to the 1 plus 2 to the 2 plus 2 to the 3. I'm going to write that as a 4 minus 1 because that's such a standardized way to do it. Or another way to say it is it reminds us there are 4 terms. Any way you slice it, the number of terms or the next power, I kind of prefer the next power interpretation. That's what goes in here. That's 2 to the 4 minus 1. You get 15. So that's another really good example. And here, we didn't have to, it came out as the next power minus 1 already, even though this wasn't contrived to be something different from 1. And that's because 2 is very, very special. And we're going to see if we can see the pattern pretty soon here. Let me blow through another few examples real quick that are of a very similar type. What about 2 plus 6 plus 18 plus 54 plus, pause the video if you want to figure out what the pattern is here. It's a geometric sequence. The common ratio is 3, and the first term is 2, so it's plus 2 times 3 to the n minus 1. Okay, let's see what we get. 2, 8, 26, plus 54 is 80, plus the next one is a 162, and if you add that in, you get 242. Okay. So what are the crucial things here? The powers of 3 are really crucial, so I'm just going to write those next to it. I'm going to write 3, 9, 27, 81. The powers of 3. Okay, that makes it pretty obvious. That's that minus 1, that's that minus 1, that's that minus 1, that's that minus 1, that's that minus 1. Okay. So once again, we found an example that, and I did contrive it a little bit by starting with 2 here, that works out very, very beautifully. That the sum of like these first 3 things, which ended with a 2 times 9, that's 3 squared, you just get the next power of 3, 27 minus 1. So here's that next power of 3 minus 1. That's really cool. Okay. What about 3 plus 12 plus 48 plus 196? Another good one to pause and see if you can see the pattern there. Common ratio is 4, and first term is 3. And again, I chose that to be 3 to make things work out in a nice way, but let's see what we get. We get 3, 15, plus 48 is a 63, plus the 196 is, yeah, is that working out? Oh, there's something, oh, that's 192, my bad. No, If you had paused, and you might have been confused. What the heck is a 196 doing there? That's a 192. 255. Those aren't super familiar numbers, but again, what are the crucial things here? This all has to do with powers of 4. The one thing we haven't written out here is simply the powers of 4, and that's 4. 4 times 4 is 16, times 4 again is 64, times 4 again is 256. Aha, again, they're just those minus 1. So, and again, it's the next power. When we use like 48, this sum here got us up to 63. The last power of 4 we used was a 16, so 3 times 16, and this is the next power. So again, so now it's 4 to the n minus 1. Okay. If you feel like you've gotten enough out of those examples, you can skip to the next video. But real quick, I'll just do 4 plus 20 plus 100 plus 500. You probably get the idea. That's 4 times the powers of 5. You get 4, 24, 124, 624. I think we know what to get. Yes, that's 5 minus 1. Yes, that's 5 squared minus 1. Yes, that's 5 cubed minus 1. And that is 5 to the 4th minus 1. So this is 5 to the n minus 1. Okay, so these are a little contrived. I don't want you to think that everything is this simple. And we saw already that there was at least one case where we have to have a denominator. Okay, and the general formula is going to have a denominator in it. But these guys are all of the same type. And you can see the pattern now. You can see that we've got the ratio is r, and I've contrived it. I've chosen a1 to be r minus 1. That seems to work nicest. Most nicely, I guess. Okay, and then the question is, can we just get it a little bit beyond that? But we really got the main thing if we know these examples. And in the next video, we'll make it more general.